Esse aqui vai para o detectors e
Yeah, it's cool.
With Professor Angela, and I'm helping her today with this seminar. The speaker today is Dr. Andrew Miller. Dr. Andrew Miller received his PhD from the University of Florida and the Sapienza University of Rome, and is now a postdoc at the National Institute of Subatomic Physics and Utrecht University, where his work is on new probes of dark matter, primordial black holes, and neutron stars, as well on machine learning techniques to mitigate noise disturbances in the legal variable data. So I think you can.
Yeah, thank you. I think this doesn't really work. Can you? Oh, there we go. Okay. Okay. Yeah. So thank you, Gabrielle, for introducing me, and thank you for having me today. So maybe we could turn this light off too. Yeah. Thank you. So yeah, thanks. So I'm Andrew. Yeah, I'm a postdoc at NICAF and Utrecht. And so yeah, I'll talk to you about how we can use gravitational waves to probe essentially mostly exotic sources. So kinds of dark matter or primordial black holes, but as well as some standard astrophysical sources like binary neutron stars or extreme mass ratio inspirals, which is the meaning of this embries here. And so yeah, I'll go through. And so basically, very simple models can describe all of these things, all these three things. And so we can use the same kinds of techniques to search for all of these different kinds of astrophysical sources. So now just a brief outline. So first I'll talk about primordial black holes, PBHs. So these are specifically light ones. So that light means actually less than a solar mass or a solar mass. So these are black holes that could exist if primordial black holes did form at some point in the early universe. But essentially, that since they're below a solar mass, there's no clear astrophysical way of producing them. This is why we call them primordial, or they're likely to be primordial if we were to see something that's less than a solar mass. Then I'll talk about extreme mass ratio inspirals, but actually mini ones. So this is essentially an ordinary astrophysical black hole, so like a 10 solar mass black hole that has an orbit around it, an exotic object that's much, much lighter. So the mass ratio is extreme. So the mass of the smaller one could be something like 10 to the minus 5 solar masses. So the bigger one could be 10 solar masses. Then I'll talk about a recent search that we've done in the most current observing run of the past observing run of LIGO and Virgo for these light primordial black holes. And then finally, I'll talk about in the future, so how we can use these same kind of techniques that I'll discuss in this presentation to look for long-lived neutron star inspirals at very low frequencies, where low frequency means between like 2 and 10 hertz, which is essentially inaccessible now with our current detectors due to the presence of all this seismic noise, the fact that the Earth is shaking at those low frequencies. So just to give you a definition of what are these long-lived sources. So as I mentioned, they can describe quite a variety of systems. So you could have neutron stars that have some mountain on them that slowly spin down. This would give rise, not in a binary system, just an isolated one. This would give rise to gravitational waves that essentially last forever. As I mentioned, these planetary mass black holes. Also, ultralight dark matter, it could form around black holes that are rotating, and it could essentially, the particles would annihilate over time, and they would emit continuous gravitational waves as the cloud depletes over time. And this cloud is macroscopic. This is a picture here. So it's actually bigger than the black hole. Then, okay, neutron star inspirals, and all of the work that I'll talk about is applicable to future detectors as well. So when space detectors fly, like LISA, essentially there'll be a lot of these long-lived sources that come from white dwarf binaries that are inspiraling forever, as well as intermediate mass black hole binaries, which are basically like hundreds to thousands of solar mass black holes that are inspiraling. And the key point is that many of the techniques that are currently used to make these detections of merging black holes, which are based on the match filter, these don't really work for these very long-lived sources. And So this match filter is something that you essentially have a model of what the signal looks like, and you correlate that with the data, and you look essentially for a match. And the correlation is maximized when the signal matches exactly what's present in the data. But this is very computationally expensive because you have to make the models, that you have to make these waveforms, and you have to basically space them. So you have to put them to populate a parameter space such that if you use one waveform and then use the next waveform, you're not missing something in between. And so this like spacing between the waveforms becomes very, very small as you look at as the source duration increases. And so you need more and more of these waveforms to populate the same parameter space. So that is a huge computational cost because each time you have to correlate this waveform with the data. And so this is why these methods can't really work for these long-lived sources. Also, you have to be sure of the model. Like you have to know that this is going to be that this will be the binary black holes that are emerging. At these masses and this position or these spins. And for these kind of exotic sources, we don't really know much about them aside from that they might exist. And so we have to have ways that are a bit more theoretically robust against uncertainties in the theory itself. And match filtering doesn't really allow us to do that. So we have to devise new methods that I'll talk about. So now why these kind of long-lived sources? So you can probe exotica, kind of particle dark matter. You can also try to constrain the neutron star equation of state if you can make a detection of binary neutron stars or even an isolated one with some mountain on it. This will give you a direct path to the equation of state. And these kinds of, even the kinds of vanilla sources that we're used to seeing now, these black holes that merge, they will last a lot longer in the future detectors. So in the future, there will be new ground-based detectors that are called Einstein Telescope in Europe and Cosmic Explorer in the US that basically allow you to look at frequencies about 2 hertz or 3 hertz or 5 hertz at minimum compared to now, which is about a minimum of say like 20 hertz. And so this means that all of these signals will last longer, and that means so even the ordinary ones like the black holes that merge, they will inspiral before they merge, and we have to be able to deal with the data quality problems that we expect to have at these low frequencies because not only will the noise be different, but since the signals are lasting longer, the noise itself is changing over the duration of the signal. So it's non-stationary, it's not Gaussian, and you also have these disturbances that appear as you're observing your signal. We call them glitches. So they're basic, and you also just have times the detector is not on. It could just turn off. It loses lock, as we say. It loses the resonance in the cavities of the interferometer. And so these kinds of the kinds of sources I will talk about today that are long-lived, the methods that we apply to these sources will also be useful to deal with these kinds of data quality issues that we will have in the future. So now how do we actually search for these signals? Not even talking about physics, just talking about data analysis. So since we don't completely trust our models, we don't use match filtering, and also because we can't afford to do it. So we actually use what are called semi-coherent methods. So this is a fancy word that just means that we break the data into slices and we analyze the data coherently, so with the phase information in each of these slices, and then combine the power of each of these slices. So in pictures, that means that you have this, so your data are broken up into chunks of the fixed duration. So this is what we call an FFT length. And so then this, a fast Fourier transform duration. And so each of these chunks is fast Fourier transformed. And then you build up this kind of spectrogram where at each time you have a power spectrum. And that's what you see here. T1 is a power spectrum at time 1, T2 is a power spectrum at time 2, etc. And you build up this time frequency spectrogram. So this is a frequency versus time map where the color is essentially the ratio of the power and this power that you see here divided by your estimation of the noise. Because essentially, since we don't know, we can't write down an equation for what the noise looks like. We have to actually empirically or experimentally determine what the noise looks like in each of these chunks. So in practice, we use some kind of running median, or but this is it depends on especially the particular method. And so what the output of this is that these time frequency spectrograms that last, this is about a month. This frequency span is about maybe like 20 millihertz, something like that. So these are long-lived signals. They tend to be very narrow band, and they last for a long time. And long meaning like, at least hours, if not days. And so this is basically what we do. And all of the methods that we use to look for these long-lived signals, they tend to work on these time frequency spectrograms. So if you notice here, there's just power, there's no phase information. So we've lost the phase when we do this, when we kind of make this spectrogram. But what we do gain is, computational efficiency, because since we don't need to worry about the phase or the phase evolution of the signal, we can, we can essentially reduce the number of waveforms that we need to search over. And also, if you have questions, just feel free to interrupt or whatever you want. Something's not clear, whatever. Okay. So now I'll shift to some physics. Talk about how we look for light primordial black holes that are so this is a binary primordial black hole system that's slowly inspiraling, and so just to give you a kind of a landscape of what's the kinds of constraints we have to compete with. This is a plot of essentially the mass regime of primordial black holes that people tend to care about, which ranges from 10 to the minus 18 solar masses to 1,000 solar masses. And on the y-axis is essentially the quantity that we often constrain when we do searches or when people look for these primordial black holes. So this is an FPBH, which is the fraction of dark matter that PBHs could compose. So you want this fraction to be less than 1. So that's why up here there's a line at 1. And so these constraints basically mean that at particular masses, particular experiments say that, okay, that the fraction of dark matter at 10 to the minus 9 solar masses can't be more than 1% or so. And so the choice of masses is, it's somewhat arbitrary in the sense that, primordial black holes could take on any mass depending on when they formed in the early universe. And so there's no reason to prefer one mass over the other, at least a priori. And so each of these masses can be essentially constrained in a different way. And you can use different experiments to constrain away the fraction of dark matter that PBHs could compose at that mass. And so the fact that we quote the constraint in terms of this fraction of dark matter implies that there are some links of primordial black holes to dark matter, and that's essentially that they could compose all of dark matter, they could compose a part of it, and if they compose a part of it, then there has to be something else that explains it, and so that's kind of what these constraints mean. But these constraints are not absolutes in the sense that they do depend to some extent on how you assume that primordial black holes form. If for example, if they form in clusters, which is a reasonable model for primordial black holes, these constraints that come from microlensing, they go away because so there are these like implicit assumptions that go into each of these constraints that make it so that these constraints are not, they're there to be taken with many grains of salt. They're not completely and always true depending on the model that you assume for how primordial black holes form. This means that you should have different experiments that probe the same mass regime as other experiments, but probe them under different assumptions of how primordial black holes form. And luckily for us, gravitational waves that allow that because if primordial black holes form in clusters, then they will form binaries with some rates, and which people can model. And so that's a way of probing this mass regime, this like planet mass, 10 to the minus 6, or asteroid mass, a little bit lower, for a different model of primordial black holes. So I will just say that so people, of course, have looked at gravitational waves from subsolar mass primordial black holes, but have basically focused on searches down to 0.1 solar mass. And this means that the binary itself has two objects that are probably a minimum of 0.1 solar masses or so. And so this is mostly because there's many reasons for this. One is because the constraints are better. So like if you look at this constraint on FPBH as a function of the mass, you can see that at higher masses, the constraint on this fraction or this percent of dark matter is more stringent. And so what this means is that the signal strength is proportional to the product of the two masses. And so when you go to lower masses, you have a weaker signal, but you have a signal that lasts longer. And so what you can do, and what is the principle behind a lot of the analysis that's done for these long-lived signals, is that you can analyze the data for a long period of time, and so you can slowly accumulate a signal-to-noise ratio because you're observing for hours or days, compared to when you look for even like these 0.1 solar mass or the ordinary black holes that LIGO and Virgo see, where they're just essentially less than 1 second that they're appearing in the data. And so you cannot gain by observing for longer for these kinds of like vanilla sources. But for the long-lived sources, we can analyze the data for longer. So this means that this mass range, which I put here, this 10 to the minus 7, 10 to the minus 3 solar masses, this really hasn't been so well constrained with gravitational waves. And that's why we chose to focus on this range. And so what the signal actually will look like in the data, or how long it will last anyway, depends on what is the two masses of the two objects, as well as what frequency that we're observing them at. So on this plot here, you see on the y-axis is the frequency at which you're observing the systems, the gravitational wave frequency. The x-axis is something called the Chert mass, which is a particular product of the first mass and the second mass. And on the color bar is the time it would take to merge. And so this down here is like 1 hertz and 10 to the minus 7 solar masses. Up here is 1 solar mass and 1,000 hertz. And so this color gradient is quite broad. So down here, these systems will inspiral for longer than the age of the universe. But up here, they will inspiral for hundreds of seconds. And so it's this kind of intermediate regime that we're interested in. So like from 10 to the minus 6 all the way up to 10 to the minus 2 or so, these signals are lasting hours to days. And so that's like kind of what we're interested in searching for. So we can model these in a particular way that is pretty basic. And the reason for this is because these primordial black holes, they are quite far from merger. So you don't have to care about any kind of tidal effects, if there's any kind of like stuff around the black holes. You don't have to care about spins, because it's expected that primordial black holes are formed with low spins in the early universe. And the way that this is kind of formulated is that you just basically assume that the gravitational waves are emitted by two objects that are in almost a circular orbit, that the orbit is slowly shrinking as time goes on. And so that basically means that the rate of change of the orbital frequency, or the gravitational wave frequency, so this is df dt, is proportional to the Chert mass of the system, and also the frequency of the system to some power. And where you have higher contributions, these are called post-Newtonian corrections. But these higher order contributions don't really matter because the system is so far from merger. And then, as I will explain later, like this kind of assumption of just this so-called zeroth order post-Newtonian correction, or PN correction, this zeroth order is actually good enough to handle even the higher order corrections. So just by assuming this model, we're actually sensitive to higher order perturbations to this the rate of change of frequency over time. And so that's good for us because, like, in these standard match filtering analyses that look at the phase evolution of the signal, they must consider all of the additional terms in this series in order to have the best of the true waveform of the signal. But since we're only doing things in power in the time frequency plane, our criteria for for like measuring a signal is different. So we don't need the phase difference to be small between two adjacent waveforms. We need actually the power to not move by more than a frequency bin in our case. And I'll explain more of that as we go on. So now I'll focus on, I guess, the first so I'll focus on Emery systems, so mini extreme mass ratio inspirals. So again, what the system is, it looks like an ordinary compact object, like a black hole or neutron star with some exotic compact object around it. And typically these Emery systems, they are sources that we expect to see in space-based detectors. So in that case, you have like a supermassive black hole and like an ordinary star that's like being whirled around the supermassive black hole and eventually plunges into it. But it turns out that if you essentially shift the masses, so you make the you assume that the primary object is not a supermassive black hole, but maybe an ordinary one, you can actually think about detecting these very asymmetric mass ratio systems now in current detector data. And so just to prove to you that that's actually possible, here's a plot that shows the gravitational wave amplitude as the characteristic strain, it's related to the gravitational wave amplitude by some order 1 factor as a function of the frequency that you're observing at. And so what's plotted also on here is on the black is essentially the time evolution of the inspiraling system. So at say like 2 hertz here, this system is 10 years from merging. At like 3 hertz, it's 1 year from merging. At 20 hertz, 100 hours from merging, and so on. And what's also plotted here is the LIGO design sensitivity. So this is like essentially the weakest kind of signals that we could see in advanced LIGO when it turns, like I think even like when it reaches its design sensitivity. And so you can see that this signal strain is much higher than the expected sensitivity of the detector. And so therefore we could actually see this signal as it's inspiraling, maybe from around here, around 10 hertz. And so this is very good. So we could actually have a chance of seeing such a system, depending on how far away it is. This is at 1 megaparsec for a system of 10 solar masses with a smaller object of 10 to minus 4 solar masses. So of course these curves change depending on what you assume the binary components are. And so when we actually do a search for these systems, we have to actually search over different combinations of this big mass and this small mass. And so that's what we do. Yes. Oh, I don't really know. I think it's like hypothetical. You do know. I'll repeat the questions. The question was, what is a boson star? I guess it's a star made of bosons, but maybe there's like some way that this actually forms. So it's not like a neutron star, but it could be some dark matter like that forms inside a star or something. I really don't know, but it's just like one of the many kinds of hypotheses that people make for this like exotic matter. But from our perspective, we don't really care what the source is. We do searches for things with certain masses. So the theorists can interpret like those masses as what they want. So I don't know much about what boson stars are. The PBHs, that they're popular, so they're trendy. So we talk about like our results in terms of PBHs. But in fact, everything I say can be generically applied to any kind of subsolar mass object. Any other questions? Okay. So I'll skip this one. It's not that important. I'll just say that the equation that I showed you before with this rate of change of frequency for the case of these like MRI systems has to be modified by some term that depends on essentially what the spin of the the primary object is, as well as what the frequency of the orbital frequency of the system is. So then a natural question is like how far away can we actually see these systems in the future with an advanced LIGO? So here is plotted a distance reach at some confidence level as a function of the mass ratio. The color is not that important. And so what you can see here is that these when the mass ratio is I guess when it's like 10 to the minus 3, so it's smaller, it's less asymmetric. You can see stars on the order of, you can see systems on the order of like 10 megaparsecs away. But for the more asymmetric systems, so like the smaller values of the mass ratio, you can only see stars at the level of like a kiloparsec away. So like the level of the galaxy. You can see these systems, I mean. And since, as I mentioned before, we're quite agnostic to what this exotic object could actually be, we can also quote projective constraints in terms of the compactness of this secondary object. So this compactness is given by the mass of the object divided by the volume in geometrized units. And so we can see at particular masses of this compact object, we could essentially constrain compactnesses between 10 to the minus 5 and 10 to the minus 1, at 1 megaparsec away, and so on, for this particular choice of system. So again, these projected constraints, they are a choice. We are choosing what systems to look at, and giving an estimate of like what the constraint would be for that system. In fact, this will change depending on what mass you assume for the primary object, what spin you assume for the primary object, and what starting frequency that you assume. So these are all dependent on somewhat arbitrary choices. But the point is that you can see them, roughly speaking, from the level of the galaxy to the level of like 10 megaparsecs away. Okay, so now I'll talk about results from a real search. We've actually done a search for these kind of like mini memory systems, except that it's so yeah, let me just jump right into it. So, but we do the search in a very like restricted regime. So what we do is we want to shit. I think the cursor stopped working. No, it works. And yeah, it works. Okay, thank you. So yeah, let me move on. So as I said before, the signal looks like this chirp, like this kind of curve in the time frequency plane. But if the masses of the two objects are, or at least if the chirp mass of the system is very, very small, and the system itself is very far from merger, this chirp is not actually very chirpy. It's more like a monochromatic signal that has a very slow frequency evolution over time. And so essentially what we can do is we can assume that, assume that these systems exist. So that means that their frequency evolution over time would look something like this, where the frequency as a function of time is equal to the starting frequency plus a very small frequency drift over time, where this frequency drift is something like a nanohertz per second. And this kind of equation describes systems that are very far from merger with very small chirp masses. And so this means that, so essentially there are searches that are already done within the LIGO and Virgo Cogra collaborations that look for this kind of signal model. It's just that they look for this coming from mountains on deformed neutron stars, where this is actually a minus f dot because the neutron stars spin down as they emit gravitational waves. But there's something special about that model. What matters from the perspective of people that analyze the data is not like what's actually causing this, this frequency drift over time, but just that you are looking for this particular pattern in the data. And then you can interpret your results in terms of whatever you want, as long as that whatever you want has this kind of pattern in the data. So it turns out that primordial black holes that have very light masses, very small chirp masses, they have a time frequency evolution that looks like this because they're essentially inspiraling forever. They're basically never making an orbit around each other. And so we can interpret results from some search that was done in LIGO and Virgo and constrain something about primordial black holes. And so that's what you see. So what you can do is what's really like comes from the kind of search, like what is the output of these searches in the case of no detection is essentially an upper limit on gravitational wave amplitude. And so that's something, so like you assume this model for the gravitational wave signal, and with that model, there's a particular gravitational wave amplitude that would generate this kind of phase evolution over time. And you can write an equation for that, and that depends on the noise and depends on your detection statistic. So with that information, you can write down what is the minimum detectable amplitude that you could see that would follow this signal model, independently of where physics is actually describing that model. And so with that minimum amplitude, you can convert that to a distance reach because the amplitude of a wave is proportional to 1 over the distance. And there's an equation for this that that for like the amplitude of gravitational waves as measured by as coming from an inspiraling system. And from the distance reached, you can get a rate. So 4/3 pi d cubed, if you assume that all of the systems are coming from anywhere in the sky, with no preference, times the time that you're observing for, and actually 1 over that gives you the rates and the rate density. And so from the rate density, you can get something that's basically independent of whether or not these systems are primordial black holes, whether they're fork stars or whatever. And so you can get a constraint on this rate density. And then when you start interpreting things like, okay, well, I want to ascribe my model to the data. I want to say, okay, these are actually primordial black holes. You can write down an equation that relates this rate density to something about the primordial black holes that is physical. So in this case, the rate density for asymmetric mass ratio primordial black holes depends on some constant that's pretty robust against some theoretical, depending on the formation mechanism, the two masses, and some effective parameter that characterizes what fraction of dark matter that primordial black holes compose, as well as what are the mass distributions of primordial black holes. So, like what is the, if you made a histogram of all the black holes in the universe, what their masses are, what would that distribution look like? You can essentially quote a result that's that's parameterized by these by this fraction of dark matter as well as these mass functions. And so since we don't know these things, we don't know FPBH, we don't know the mass functions, we can just quote the constraint in terms of this model independent parameter f tilde, and that's what you see plotted here. On the y-axis is this f tilde, on the x-axis is the secondary mass, where you assume the primary mass is 2.5, for no good reason other than the fact that we've observed stuff with this mass. So it's reasonable to think that maybe there's something else orbiting around, there could be a system that's with a very light companion orbiting around it. And so this number is a fraction as well, since it relates to a fraction and it relates to PDFs. So this number should be less than 1 ideally. But in this case, the detector is not sensitive enough, or our searches are not sensitive enough, so we get a constraint that's above 1. But within a few observing runs, we could probably push this down to below 1 and actually have a physical constraint on this f tilde parameter. Okay, so now I'll talk about, so given that we can't make a physical constraint here, if we now consider higher mass systems, so not these like asteroid mass, so not 10 to minus 10 solar masses, but say 4 orders of magnitude larger. So can we make a physical statement about those? And so that motivated a search that we did for these planetary mass primordial black holes in the first half of the observing run. I just want to check the time. I think we started late, but okay. Maybe 5 more minutes and then I can take questions. So let me just finish. I will just say that we have a method to look for these systems. I don't have time to go into it. We did a search over this chart mass versus frequency parameter space that you see plotted here. We had some candidates that looked like real signals, but then they were not. And so we have ways of essentially vetoing these candidates. We can compare them with no noise lines to see if there's some overlap. We can analyze the data in one detector, get a bunch of candidates, and then see if we get the same candidates in another detector, and do coincidences between them. So we have ways of dealing with this. But I'll just skip to the results and just say that this is a lot going on that I don't want to explain. But essentially, like at masses that are below 10 to the minus 5 solar masses, we can actually get a physical constraint on this parameter f tilde, so that is going below 1, which is around here. And so this means that this kind of result, we are sensitive to primordial black holes that would be merging around like 10 kiloparsecs away or so. And we could place a physical constraint on this effective parameter, or essentially a physical constraint on the fraction of dark matter that PBH could compose. So I think, I'll just highlight that you can also apply these methods to future detectors and just say that there are many problems that we expect. So like many signals appearing at the same time, and noise non-stationarities and gaps, and many problems. And so these kind of methods can be used to look for neutron star inspirals, essentially lasts very long times at low frequencies. So here you see a plot of the frequency versus time of a BNS inspiral. You can see it lasts like half a day as it's inspiraling between 3 and 10 hertz. So this is important because first of all, you can analyze more data, so you can get better signal-to-noise ratio, but also you can use this time that you're analyzing, you can use this time here to obtain a detection of a neutron star inspiral, and then warn astronomers that hey, there's going to be a merger, like 2 hours from now. And so we studied, how we could possibly do this in a very simplistic case. But we can basically, warn astronomers at a certain duration ahead of time. And we can also provide some sky localization, because when the signal lasts so long, the point is that the relative motion of the Earth with respect to the source starts to matter. And so like as the Earth rotates and revolves around the sun, this induces Doppler modulations of the signal. And since we can observe for, 50,000 seconds, it's like half a day, we can actually start to resolve these modulations, which help us localize the source somewhere in the sky. And we can do this in addition to the kinds of methods that are already used in these typical black hole merger situations, where they use the delay time between when signals arrive at different detectors to triangulate the location of the source. So yeah, and we can do comparisons. So I'll just conclude by saying that like this very simple model of a power law or of a quasi-monochromatic source can describe many kinds of both exotic and non-exotic systems in more than I had time to discuss today. And we are working to be prepared for future detectors, so to deal with the kinds of noise problems that we expect to have. And yeah, that's really it. So thank you for listening, and I'm happy to take questions.
Very slow variations of frequency. Can you disentangle the variations of the frequency due to the source? And for instance, if your source is in a closed or open orbit in a multiple system?
Okay, so the question is, for the slow varying frequency systems, can we distinguish between like if it's what we actually think it is, and then this, I forget, what could you?
Suppose your source is in a binary in a multiple system and you have a closed orbit.
Okay. So if it's in a binary system, it has a closed orbit. So yes, so like the evolution of the system is very important. So if it's quasi-monochromatic, so if it's truly like, so let me go back to this. So if it truly looks like this, like if this model describes both your closed system and like a neutron star that's like accreting matter and spinning up slowly, then no, we can't disentangle from the gravitational waves itself. But say that we can use astrophysical probes, so like we know there's a pulsar here, so or we know we're looking in some cluster where we don't see neutron stars. So yeah, and the fact is that these orbits also have this this frequency evolution. So if we're observing them for long enough, then this kind of chirpy behavior will appear, and so then we can use that to disentangle. But basically, the sources are pretty unique. Like the masses and different masses, different spins will get different imprints. So.
What is the perspective of detecting non-inspiring sources? I mean, like disruptions and things like that.
Tile disruptions. You mean like at the end of the inspiral?
Accretion in a mass backbone of the star, for instance. The kind of source that IceCube detected.
Oh. Okay. So the question is, what are the prospects of detecting sources that I guess that are not inspiraling or merging? They're just like accreting, like a black hole's accreting from something else. So I don't think we really think about those sources. I don't know if it's that the accretion, just the quadrupole moment is too small, or the system. But yeah, we really don't. We have systems like if you have like one neutron star that's accreting from something else, then we do look for these. Neutron stars that exist in a binary system where one's a neutron star, one could be a black hole. that it's accreting something from. But I think in the way you describe, I don't think that we're not looking for the accretion. Like we're looking for the effect of the accretion on the waveform itself. So I don't think maybe some people have done something with it, but I don't know about it.
Professor Elizabeth has a question.
Okay, please go ahead.
Is it my turn? Can I ask?
Yes, go ahead.
Okay. Well, very nice talk. Thanks. And my question regards the your models. From your models, you can directly constrain or provide robust constraints on dark matter distribution, right? It seems to me that you can provide some constraints for dark matter distribution directly from the model. On the other hand, you expect that gravitational waves can help to provide further constraints, or in other words, can provide constraints out of these observations of these systems, right? But at this stage, how constraining the observation solely based on gravitational waves could be, could provide really strong constraints besides the constraints that you can infer from the model of the formation of these binary systems. Did you understand my point?
Not entirely, but are you asking about constraints on FPBH or on the dark matter distribution or?
Yes, of course. Mm-hmm.
Okay. Well, I guess I could show this plot again. So so you're asking to what extent can gravitational waves constrain different parts of this plot?
Exactly.
Okay. So they can. So like this curve here comes from these gravitational waves that come from. Oh, would you mind muting, please? Okay, thank you. Oh wait, can someone else mute? It's okay better now? Oh, I think it's okay. I think it's okay now. Okay. Yeah. So so already you have constraints from gravitational waves that cover this mass region, so above a solar mass. So this comes from like people that try to interpret the mergers that we have seen so far rising from PBHs. Yeah, I don't really know what they do exactly, but I think they probably compare the rate densities that they are inferred from these observations with the rate densities that are written down for primordial black holes, and they use like the disparity between these two to place some constraint on the FPBH, which is probably why you see this curve here. And then that's down to like maybe 10 to the minus 2 solar masses. And then the results, which I guess kind of skipped through from our search about these primordial black holes, like you can in fact get this this F tilde is like FPBH, but you can essentially get constraints below 1 when you talk about systems of 10 to the minus 6 to 10 to the minus 4 ish solar masses, which would then cover let's go back here, which would then cover, like this region here, which microlensing has pretty well constrained. But again, like if the PBH is forming clusters, then these constraints are not so stringent anymore. So I mean, we are making progress in like trying to tackle this mass regime with gravitational waves. It's just that it's a combination of the fact that the signals are weak and the fact that the computational cost of doing these kind of searches is very large, and so this prohibits And also, and this prohibits going like below, say, like 10 to minus 9 solar masses. But people are thinking about ways of doing that as well. Did I answer your question?
Yes, I guess so. Yeah, thank you so much. Yes, this was exactly my point. Because you have, on one side, you have the predictions from the models for the primordial black hole binary systems, and these mini black holes as well, of different masses, and on the other side, what the current instruments can do. And yeah, I think this was more clear now.
Yeah,
Mm-hmm.
no problem. Now, there's a big limit to what the instruments can do and what the data analysts can do because of just like the weakness of the signal and the computational costs. So that's kind of why you see this. The instrument is just not sensitive at lower frequencies. I think this is why you see this this curve here. This is kind of like where the bucket is in the sensitivity curve of the detector. And so you have some dependence in these curves about the instrument itself.
Right. Mm-hmm. Thanks.
No problem. Are there any other questions? Okay, no problem. Thank you.